my pleasure to introduce our speaker today, Professor Ashley Payne from the University of Michigan. And Ashley's been hopefully visiting with a bunch of people today. I think she has collaborations already with several people in the room and in the building for sure. Ashley has a geology background. Was that at University of Texas or somewhere else in Texas?
University of Texas.
University of Texas. Where are you from originally?
Austin.
Oh, Austin. Okay, an Austinite. So that's like a Madisonian, except at a lower latitude and less snow. And after finishing at UT, Ashley went to UC Irvine and worked with Gudrun Magnusdotter on atmospheric rivets. And Gudrun's portfolio is very wide and includes lots of things, both theoretical dynamics and applicable weather systems work. So that's what Ashley was doing there. And then she went to Michigan on a postdoc, right? And that transitioned into your current faculty position at Michigan.
Yes.
Sounds like. And then this is the beginning of your second year, I think you told me. Yeah. So a new faculty member at Michigan, and doing some interesting work on atmospheric rivers. In fact, an atmospheric river intercomparison project that's really a big deal, trying to look at how these things are portrayed both in the present time and also in climate models, and with a peek toward the future, what might be different about them as we move forward. And as I mentioned, there's some collaboration already with people in the building, I think, because Ashley's working on a proposal, the Earth Venture mission. Is it NASA or NOAA, or both? NASA, okay. And so it's widely applicable. It's going to be looking at wind vectors and various other things and trying to remotely sense information about 3D atmosphere, but broadly applicable, but not particularly to the atmospheric river projects right now, although that may be one of the applications in the future. So it's a great pleasure to have you here, Ashley, and we're looking forward to your talk, so welcome.
All right, well, hi everyone. So I'm an assistant professor in the Department of Climate and Space Sciences and Engineering, formerly known as AOSS, if anyone's familiar with the long history of this department at Michigan. And what I'll be talking about today are atmospheric rivers over the North Pacific Basin. It's a pretty kind of bland title, and I'll be talking about a lot of things, so this was the best approach I came up with. So, okay, here we are. And so first I wanted to talk about is what are atmospheric rivers, or actually even how can we look at them. And so what this is supposed to be, there we are. This is an animation of atmospheric moisture using Merit-2 reanalysis. And so you can see this band of tropical moisture here, and then extending towards the west coast of North America, you can see this kind of what seems like a continuous band of moisture extending over the North Pacific. And so this is total precipitable water, but if we move forward, what we see here is the magnitude of moisture flux or integrated vapor transport. Early in my career, I was using moisture flux, so you'll see me say MF and IVT. IVT is the more correct acronym here. But if you look at this band of high moisture, you can see superposed on it, you have this basically intense band of moisture transport. And so if we look at what this looks like in a cross-section, what we have here is this cross-section here and the vertical right here. And you can see this, this moisture transport is occurring in the lowest 3 kilometers of the atmosphere. And this is a nice schematic from Marty Ralph in 2004, based on observations over the North Pacific. And in terms of the amount of research, the North Pacific Basin is definitely kind of the source of a lot of this research. So, when I'm talking about observations, I'm generally talking about the North Pacific. So moving forward. Just before I go into kind of specifics of my research, I wanted to kind of, convince you that these things do occur globally. I think sometimes the perception is that they only occur and impact California. And so what this is a nice simulation from Maxi Viali in Chile showing a simulation of an atmospheric river case study that made landfall and impacted the Andes. And this single event resulted in roughly 10 inches of rain over, I think it was a 36-hour period. Oh yeah, I have it written out. I'm bad at reading and talking. Over a 36-hour period, so a lot of rain over a very short period of time. If we look to the south, this is a study by Irina, yes, long name. She's a great researcher, does a lot of work at high latitudes. And her work here shows 4 seasons of observation showing the impact of atmospheric rivers on accumulation events over East Antarctica. And so you can see those in kind of the filled red circles here. And then moving over to the tip of South Africa, you can see that a large percentage of total wintertime precipitation is actually associated with ARs. And this is work in Blamy et al., and it's actually published at this point. And in terms of impacts from that drought, the extreme variability in these things making landfall, that region is almost recovered in the present, though this may not be due to atmospheric rivers themselves. These things don't only occur along the western coastline, so there is some evidence that this extreme rain event that occurred in Japan may have been due to an atmospheric river, and so you can see this orthographically forced precipitation here, with the colored contours here. And then there's recent work from Dwayne Walliser and Ben Wan in 2017 showing that a large proportion of European windstorms were actually associated with the presence of an AR. And so this data was between 1997 and 2013. So not just precipitation hazards. And then finally, there is some evidence, though again, depending on how you define these things, there is some evidence that a large proportion of annual flood maxima over the Midwest may be due to these atmospheric rivers. So this is work from Dave Labers and Gabriele Villarini out of Iowa. So what I'll be focusing on here is my work over the North Pacific. So moving forward. So talking about these things as extreme events for the West Coast, what this graph shows is accumulated precipitation for that animation I showed on the first slide. And this is accumulated precipitation between November 5th and 7th, 2006. And you can see it's quite a lot of precipitation. And these massive extreme precipitation events, they've occurred through history. So there's some evidence that an extremely wet winter in 1861 to 1862 that resulted in this inland lake in the Central Valley of California was actually due to a series of atmospheric rivers making landfall. And some of this evidence comes from paleoclimate records from the region, with kind of the assumption that when you see these basically large precipitation events, they are likely due to atmospheric rivers, so keep that in mind. And then here's an event in Southern California that may have been due to an atmospheric river in 1938, widespread flooding in Anaheim and Burbank. And then the event that I showed on the first slide, this November 6th, 2006 event, you can see the impact that it had on land. And so also in terms of, kind of putting these in context, what this shows is a comparison of the precipitation extremes between what we see in the east and south to what we see in California. And a lot of these high points that we see in the south are due to tropical cyclones making landfall. But you can actually see some of these red points over here, so more than 500 millimeters over a 3-day period. These are tied to atmospheric rivers. Okay. And then in terms of the amount of precipitation that falls, what this shows is the amount of precipitation needed, so half of the wet season precipitation that's accumulated over this region. And you can see particularly along the coast here, you get half of this precipitation accumulated over around 10 days, and then as you move up the coast, up to 35 days. So this is a very short period of time to accumulate this precipitation. And if we look at variability of basically these intense moisture transports impacting the coastline, you can see that there is large variability in the landfall location. So what this shows are basically anomalies of IVT along this coastal transect. And these are seasonal averages from 1980 to 2015. And you can see the large variability there. And if we focus on a single season, without even going into definitions of what an atmospheric river is, you can see this large variability in these basically positive anomalies of IVT along the coastline. And I'm leading up to all of this just to say that in terms of issue for water managers, you have these things that potentially might dump a lot of rain over a short period of time. Water managers are very concerned about, hey, how do we plan for this? And so there's a lot of work being done to try to, identify and decrease the uncertainty in forecasts. And what you can see here is the RMS error in landfalling location and forecast lead time on the x-axis. And you can see as you go out to longer lead times, you have pretty substantial errors in the landfall location of these events. So for example, if you're in San Francisco for the AGU meeting, and there's a forecasted atmospheric river that's supposed to make landfall, and the AGU organizers are like, oh no, there's an atmospheric river, they want to plan a week out in advance. It could be that this atmospheric river doesn't actually make landfall up there. So these are things that people are very concerned about. Yes?
Right. Just two quick questions. You mentioned water managers are interested, obviously, in the latitude. Where's this rainfall going to occur once the river impacts? Is there also considerable error in the temperature structure at landfall, so that whether it's going to fall with snow versus rain?
Yeah, so the rain on snow events that are associated with these. So that's not actually something that I look at, but I know there is a lot of interest in that, particularly as pertains to climate change and how is the vertical structure of these going to change. Possibly, though I can't quantify it like this.
And the other question is, how to interpret the 0-day forecast lead time error? I mean, it's almost up to 350 kilometers. What's that?
Yeah, that's a good question.
Is it an analysis error?
It might be. This is a question that I had on a previous talk as well when we used this graphic. So I'll get back to you on that. But the paper is Wicked Owl 2013. All right, so just to broadly outline this talk. So the first part of this is how do we actually identify atmospheric rivers? So it's only been recently that an AMS glossary definition has been included, and this is after 2 massive town halls with a lot of people with a lot of opinions trying to come up with a very short description. It's very vague. So how do we identify these things? What influences AR behavior prior to landfall? So a little bit of my previous research. And what do projections say about their response to climate change? So I'll be jumping around kind of chronologically in my own research journey, so bear with me. Okay, so what does landfall mean? So if we're looking at this is an animation of the magnitude of integrated vapor transport in Merit-2 reanalysis. And what I've shown here is, rather than highlighting the intensity of these various transports, so that's all in gray, what I'm showing instead is a static threshold on IVT set at 450 kilograms per meter per second. And you can see, if we went in here and we were just like, okay, we're going to use IVT and, just some threshold, we're going to be identifying a lot of things that aren't necessarily atmospheric rivers, especially people who, look at tropical cyclones. They're like, no. We're identifying a lot of things. And so if we're trying to develop a detection algorithm to try to understand what's happening on climatological timescales, this isn't great, right? And so what I'll show first is my approach for detecting atmospheric rivers, and then I'll go into some results from this intercomparison project that I'm a member of. So how I approach this, I was interested in kind of large-scale dynamics that influence AR behavior at landfall. And so I'm interested in landfall. All right, so I focus on this region that kind of hugs the coastline of the western coastline of North America. And for each time slice in this data set, so here I was using mirror reanalysis, I quantify two things. And this is a centered region just along this transect. What I do is I take a zonal average for that transect, and I look at the zonal average of IVT or moisture flux. And I also look at I think this is zonal average precipitation. And so you can see that we have this peak in IVT that is co-located with kind of where this thing's making landfall. And so we have our peak moisture flux, or IVT. And then around that peak moisture flux, I summed up the precipitation around it. So trying to get a sense of the precipitation impacts. Of course, this is reanalysis, so I'm stuck in model world somewhat. I acknowledge that. Okay. All right, so what I'm showing here are 3 hourly time steps sorted according to this peak moisture flux. So this one number taken from each time step. And here we have our maximum moisture flux at one point along the y-axis. And what I'm showing here is the precipitation for each of those time steps, and you can see it scales fairly nicely with this peak moisture flux. And to quantify a landfalling event, I take the 85th percentile of this peak IVT. And then I also put in some thresholds based on observations for the North Pacific. I say that the integrated moisture needs to be greater than 2 centimeters, and there needs to be some sort of low-level wind component. So we're not interested in, when you have a warm conveyor belt, you have vertical ascent, right? So I'm interested in what's happening in the lowest part of the atmosphere, okay? And so what this shows is for a single winter season, the landfall locations of these various events that I identify. And to show what I'm actually identifying, so I've boxed an event that's in this animation right here. And so in the previous slide, what I was showing is basically the identification of atmospheric river conditions along the coastline, right? Well, that's not really getting at kind of this complete event as it makes landfall. Duration of these things is important. Like basically where they make landfall and how long they stay in one spot is important. So I have additional criteria that kind of separate out these AR conditions into AR events. So I can look at multi-time step features on a climatological timescale, or attempt to. so this is my approach, and I wanted to explain this just to give you a sense of how other people approach this, and not to scare you too much, because you're going to see a wide diversity. All right, so comparison against other ID methods. So after the two town halls and you know, this push to get an AMS glossary definition, the Atmospheric River Tracking Method Intercomparison Project, ARTMIP, was basically started. And this was our first kind of suite of algorithms that we looked at. And what this map is showing is the spatial extents of these various algorithms. So for mine, I'm focused on the North Pacific. I don't really care what's happening in Europe. Who cares? Everyone cares. But yeah, so I was very narrow-minded, and I'm only looking at the North Pacific. You can see that there's other algorithms that are regional as well. So some that extend over the entire North Pacific basin. Some that just hug the coastline, right? So they're only looking at the occurrence of air conditions along the coastline. There's others, so this Alex Ramos 2016 algorithm uses a series of lines of longitude to define thresholds, and his group is mainly interested in atmospheric rivers making landfall in the Iberian Peninsula. There's others that focus on Ireland and the United Kingdom, you know, wide variety. There's also other algorithms that are global in extent. So I'm only showing a small portion here because these were the ones participating in our proof of concept. Yes.
Would you consider a strong warm upglide sector moisture pulse in the Midwest to be, if it's above 85 percentile for that location, would that be included in atmospheric river definitions?
I would not,
No.
but other people do. So again, this is, it's messy, I think, over that region. And so this is an area where, you know, some people do have climatologies that show these things. In terms of you know, just features that bring a lot of moisture to a region, I think it's worth researching in its own right.
Like you could define a line segment east-west, and what's the flux across it?
Yeah, yeah, and some people do that. And there might be a small portion of these things that are identified that are atmospheric rivers. I can't speak to it, but my first sense is a lot of these define atmospheric rivers over that region, and I think it's mostly due to the large amount of moisture that's over that region.
Is it really honing in on a particular synoptic pattern where you're upstream of the ridge but not quite in the trough, and there's this preferred diagonal stripe?
Possibly.
Is that
Possibly.
implicitly?
Yeah. Okay. Oh, sorry, one sec. Yes. So this is, these are results from a 1-month proof of concepts in GMD that Christine Shields led. So this was basically us trying to see if comparing these algorithms even meant anything. If we were all, you know, perfect and identifying the same thing. So, yeah, the shading really does not come out here. So what this shows is a strong atmospheric river and what some of these algorithms identified as a weak atmospheric river. Again, once you get to the kind of the weaker ends of IVT, these may or may not be atmospheric rivers, but you know, we're just trying to pick something. And what this shows is days in February 2017. And on the y-axis, we have these moisture flux anomalies. So what we're trying to look at is along this coastal transect, you know, when we have these positive moisture flux anomalies, there's something going on, okay? So how well do these various algorithms identify something going on? And so what this shows is for the subset of algorithms that look at the North Pacific, you know, how well do they do in identifying this event and that event? Sorry, the shading's very bad. And you can see that some do better than others. There's some that are missing. So this is a Sellers et al. 2015. this is a very high threshold, and so with this weaker event, it doesn't detect that, right? So there's some variability in what algorithms actually detect. Okay. Oh, yes.
So what do you do? It looked like your algorithm went up to like 60 north, is that right?
Yes.
So what do you do for, that's pretty high latitude. I mean, are you missing some events up there with your threshold?
Likely.
Okay.
Yeah.
So then, because I know that like Arena and Mattingly both have like an adjusted line, so I didn't know if you're adjusting with latitude. Or...
Yeah, so this is actually something that Arena is going to be looking at and trying to see how well they perform up there. Yeah, I think, if I were going to redo this, I was really only looking at this region, so I don't know why I went up that far. It likely brought down the 85th percentile threshold that I was using. All right, so just to show a structure of what ArtMyth is, this is our experimental design paper published in 2018, showing proof of concept and putting out project requirements. This is our Tier 1 overview paper that I'm putting 2019, but we just submitted our first revision. And this is led by John Rutz. And here we're quantifying the uncertainties due to the choice in AR identification and the various tracking methods. And then where we are right now, and I was actually at a workshop just last week at Lawrence Berkeley, is this Tier 2. So I'm leading a C20C plus project where we're looking at comparison of catalogs between two climates. Travis O'Brien, soon to be at Indiana University, is looking at a series of catalogs using CMIP 5 and a small number of CMIP 6 models. And so these projects on Tier 2 are optional, so not all algorithms that participate need to actually, do anything here. They only wanted to do the first few, but they're science driven. So for mine, I'm looking at how AR climatology impacts may change in the future. That's my focus. And to just show some of the science questions that we're pursuing with this project, how did various treatments for moisture thresholds affect climate change signals? How do different methods lead to uncertainty in understanding thermodynamic and dynamic mechanisms of AR changes? And with the shifting baseline, what are the appropriate metrics for model evaluation? And this last point is particularly tricky. So just to give a sense of what I'm talking about, say you have this distribution of, let's only focus on IDT in the present climate. If we're looking at a threshold that sets a particular number, so here's an algorithm that sets a threshold of 250 kilograms per meter per second. They say everything above that and with some other criteria are an atmospheric river. And then another type of algorithm that uses a relative threshold. So here, the 85th percentile of some distribution of IDT. So we have our two in the present climate. Wow, I hope the people in the back can see very, very light things. So I still have the present climate here. All right, so now we're in a future climate, and there's some increase in IDT, simply in part due to increase in atmospheric moisture with warming, right? So we have an increased distribution of IDT. All right, well, if we look back at our two different approaches, our first uses an absolute threshold. So here's our absolute threshold based on the historical and the present climate. And then, our second set of algorithms is basically using a percentile threshold. Some use a percentile threshold in the current climate, some use a percentile threshold in the future climate. And what really makes these things different is the focus, right? So if we're focusing on atmospheric rivers as things that cause extreme precipitation and or wind damage, all these things, we might not want to shift this threshold. If it rains, So keeping this threshold with the current climate, it might be the right approach. With the relative threshold, there's some benefits. So first, it's adaptive to various regions. So, this 250 kilograms per meter per second value is specific to the West Coast, particularly for inland penetrating atmospheric rivers. Well, this value is actually very low for anything falling along the Iberian Peninsula. So, that the algorithm might not do so well there. So if we have a percentile threshold for the current climate, this could be adaptable. But also, if we have our 85th percentile based on the future climate, are we actually looking at a shift in the distribution of these features? So starting to get at, what is the rarity of these events? Okay. And so to make you very scared, this is the large diversity of atmospheric river detection algorithms that exist in the literature. And I was joking with a few, it's almost like a rite of passage to develop your own as you start this research. And I've split these up into absolute thresholds and relative thresholds just to give you a sense of where these various communities fall. And then I've also included two down here that are machine learning thresholds. And there's a very fun project that I think this department would be interested in. Researchers at Lawrence Berkeley National Lab are interested in having expert identification from the community. So it's a website where you can actually trace out what you think is an atmospheric river and what you think is a tropical cyclone. And they'll use this as a training data set for their algorithms. So kind of cool. I wish I had the website, but if you're interested, email me and I'll send them on to you. Okay, so even within the relative thresholds, there's various ways for dealing with, where does this percentile come from? Is it latitude dependent? Is it based on some zonal anomaly? Is it based on anomaly based on the climatology? Is it latitude independent? All over the place, right? So when we're writing this paper, it's actually a huge challenge to come up with a way not to shortchange any one of these algorithms, because we're all technically looking at the same thing, we hope. So coming up with a very compact way of summarizing this information was the topic of 3 hours last week. So yeah, we're still dealing with this. But to give you some sense of relief, what this shows is a comparison of various algorithms identifying ARs for the West Coast. And what we're looking at is one point along the West Coast. So this is, there's a meteorological station at that point. And what you can see is, it's Russian River, starts with a B. You should know. No? Okay. You said at summer school. Okay. All right. Yeah, so it's just south of San Francisco. So what this shows is basically a striking similarity in the climatology of these identified AR events when we're only focusing on this one point along the coastline. And what I've outlined here is just to, the same threshold in all of these, in each of these panels, just to show, what the various thresholds do for the algorithm. And you can see, some of them, this one, for example, identifies a ton of events, right? So when we're looking at this composite, it's pretty washed out. But in general, you do get kind of a similar orientation. Breaking this down, however, into what do algorithms identify well and what do they not identify well is something that I think would be pretty valuable. And the data's there. So the data for MERA 2 is released as soon as we get the official acceptance notice for the Tier 1 overview paper. And this is the Rutz et al. 2019. All right. right, so, how much time do I have? Oh,
25 minutes
no.
left.
25, okay, all right. So then, finishing up with our HIP, I'm in my first segment of the talk. So do we see robust shifts in AR distribution, variability, frequency? There's a lot of literature that exists where each person uses their own algorithm to look at impacts in the future. Well, how robust are those results? And also, a thing that I'm particularly interested in, what's the change in the flood potential of future atmospheric rivers? So, I'm talking with some people who work in they're in the Department of Civil Engineering. So, if we build our various flood control structures to a certain climate, what can we expect in the future? So this is something that I'm very interested in. Okay, that concludes the first part. All right, so going into what modifies the intensity of these atmospheric rivers before they make landfall, focusing on the North Pacific. This is work that I did with Gudrun at UC Irvine, looking at a subset of atmospheric river events that were particularly strong and making landfall along the west coast of North America. And so what you can see here are basically tracks of these atmospheric rivers across the basin. And what I'm showing in the next few slides are a comparison of the strongest events and the weakest events from this group. So there's 11 in each group. All right, so just to guide you through this is like a multi-layered figure, which is very common for our science. So each of these boxes will have a single composite, and what you see below is a centered composite based on the centroid of a detected feature over the basin. The shading right now shows moisture flux, or IDT, and you have our strong ARs and our weak ARs right here. Okay. Now what I'm showing is light gray. This is sea level pressure, and you can see in a comparison between the strong and weak ARs, you have a much deeper low pressure center to the north, and you have this persistent high pressure center to the south. Okay. Oh, yes.
Sorry, is there a formal definition for the Pineapple Express? Or is that just a kind of fun phrase to use?
So I think some people define Pineapple Express as, having it's a particularly warm atmospheric river that's sourced near Hawaii, basically coming up. Yes.
Just a point of clarification, your definition is based on landfall and precipitation. How are you getting these upwind composites?
Yeah, I should have explained that. So I identify time steps as AR time steps,
Okay.
and then I trace these features back before they make landfall.
And when is the feature no longer an atmospheric river?
Let me go back to, where's my mouse? Sorry, give me a sec, I'm having,
So like you had that one that was the integrated
Mhm.
moisture flux.
Yeah, so here, so let's go back to here. Okay, so I'm identifying landfall, right, 1 point. So let's say landfall is today. Okay, so then what I do is, I'm going backwards in time. I basically trace this thing out. So okay, so today, right? I trace the spine of the AR feature back over the basin. I make sure it's a certain length. You don't want anything too stubby. Okay, and then I step backwards in time. And I have this overlapping feature in time. So this is the same event, and I do the same. It has to be above, this, what is it, the threshold? I think it's the, 85th percentile threshold. So it's above a certain threshold in IDT. It's associated with this low level wind, and it has a certain amount of moisture associated with it. And so then I trace it back again, make sure it's long enough, it meets all these criteria, and it overlaps with the previous one. And And so I keep doing this through time. And then I have my events.
Excuse me, and then to composite, you take some sort of centroid?
Yes, so, go back here. So what this centroid is if you have, for example, if you just have a map of the North Pacific, right? And let's say this is binary, right? You have zeros and then one where you have this ID. There's a image processing toolbox that you can use and apply to this feature and pick out the center of that feature. And so what these composites are based on is the centroid of each feature, if that makes sense.
Yes, so it doesn't matter what the orientation, if the river is oriented more north-south versus east-west. That's probably why this gets kind of smeared out. It's not as
Yeah.
distinct as
Right.
an individual case.
Yeah, so basically I'm looking at, this moisture transport has to be oriented in the same direction, but yeah, it can be oriented more forward than eastward. Yeah. Okay. All right. Okay. So going back to these centered composites. So here we have our deep low pressure center to the north and this persistent high pressure to the south. For these strong ARs and our weak ARs, not so much. Okay. And then adding on top of this potential vorticity, dark gray, I'm using 200 hectopascals. If I could talk to Mira reanalysis, this would be on 350K, but it's on 200 hectopascals as an approximation. And for our strong ARs, you'll see in a second, you start to, as this thing progresses, you see the development of Rossby wave breaking, but even now you can see some breakdown of the PV gradient in the Pacific. And then finally, looking at the 200 hectopascal wind speed, so you can see this co-located upper level jet with each of them. Okay. And this is somewhat of a messy picture, so apologies for that. All right, so we're stepping through kind of the lifetime of these centered composites. So moving towards the coastline, you can see this sustained high pressure center to the south, the appearance of this Rossby wave breaking in the East Pacific. A little bit of a messier picture with these weak ARs. Is this really, am I only identifying ARs here? But if we look at our strong ARs, there's some pretty consistent characteristics here. And as we make landfall, we have our appearance of anticyclonic Rossby wave breaking. And so this tells us a few things. So these are associated with, likely a strong extratropical cyclone. And so breaking this down, not all extratropical cyclones are associated with this low-level moisture transport. But in this case, we do have this correspondence here. And so taking this a little bit further, looking at basically the frequency of occurrence of anticyclonic Rossby wave breaking, comparing kind of two sets. So ARs where the threshold in IDT is set at the 85th percentile, and ARs where I increase this threshold, so potentially stronger atmospheric rivers. And looking at the kind of this anomaly, so ARs minus the climatology over this location. And what you see over the top is the kind of the climatological Rossby wave breaking frequency. You can see that the ARs are mostly associated with this anticyclonic Rossby wave breaking, so right here. The shading is the frequency of anticyclonic Rossby wave breaking. Apologies. The strongest ARs, you see this kind of these more saturated colors. So you have an increased frequency of anticyclonic Rossby wave breaking with these stronger events, which is encouraging. And these changes in Rossby wave breaking, they can actually be indicators of AR variability and change. So, you know, there's some research from Meredith Fish that shows kind of these occurrence of AR families, so these things making landfall one after the other. And so if we're looking at hydrological impacts, you know, these are things that, you know, water managers would be very interested in. And so we see this correspondence with ROS wave breaking, you know, it kind of follows, you have this breakdown of PV gradient, kind of this following event here. So this is one bit of research that is particularly interesting, yeah.
Do you know if there's any correspondence between the strong, ROS wave breaking strong events and then downstream in central North America, cold air outbreaks in November and December?
I don't know actually, but I do know someone very interested in that, and that's Lance Bozart.
Oh, yeah, okay.
Very interested in
Yeah.
this. And so he was also at the summer school, there's the atmospheric river, summer school and colloquium, symposium, yeah. So Lance Bozart was there, and we had some pretty good conversations about his work. Okay, so in the interest of time, I'm going to skip the next part of this and go into here. All right, so I wanted to bring up this because it relates to kind of the next project that I'm doing with ArtNIP. So looking at the climate change signal with ARs. And so this is some work that I did in 2015. So for those of you working with CMIT5 data, you know my struggle. This is, you know, a ton of models. I think that this is 28 different models, daily data. And I'm comparing the historical period to the end of the century. And what you can see here is basically the frequency of AR occurrence in each of these models over the historical period compared to two different reanalysis data sets. And, you know, this is a postage stamp graph. It's very hard to see any hard features, but you know, from a distance, you can see that these models are generally resolving AR-like features. And I say AR-like features because the resolution in these models is pretty coarse. And we're looking at some pretty fine-scale features. Okay, so going to the next step here, this is an evaluation that I did to see how well these models actually capture these events when they make landfall. And so we have each of the models on the x-axis ordered from the coarsest resolution, so 3.7 degree, pretty coarse, to the highest at 0.7 degrees. And on the y-axis you see total count, okay? And what I'm showing here is the comparison of each of these models, the total count of AR days identified in each model, compared to the two reanalysis data sets. And you can kind of see this convergence as you get to higher and higher resolution. So you can see that this model performance is generally dependent on the resolution of the model you're using. Pretty basic result, but not something that has been shown up to this point. Yes?
Do you find that, I'm assuming spatial resolution matters a lot more than time resolution, but do you find that like with the new ERA 5 and like now that you have hourly, I don't know how much hourly versus 6 hourly would impact atmospheric river.
So that's actually something that we talked about last week. So there is a new project that's going to be led, I think, by Allison Callow. I think she's at Goddard. And she is interested in comparing a number of reanalysis data sets, especially now that you have hourly resolution. The issue is storage. It's very difficult to look at that number. For me, I've always used 3 hourly resolution, and I haven't run into too many issues, especially since I was looking at overlapping features through time. I haven't had too many issues. Some people use 6 hourly, but I think they're looking at more statistics along the coastline. So, but I haven't looked particularly at higher temporal resolutions.
This is an interesting comparison. I'm curious if the reason that as you get to higher resolution, you get a better match is because the rivers themselves, the abstract rivers themselves were defined based on higher resolution data to begin with.
Mhm.
And so you can't expect I was wondering if you were to downscale the highest resolution ones with your previously, well, I said with the same result. Is there a way to flip that so that you could see if they were all at the same common resolution, you would be able to?
Yeah, that's actually a good point. That's not something we did here, but if I were to take up the data again and dive into it, yeah, I think that would be interesting. There's some new research coming out of similar to the West Coast. I want to say, oh yes, Ben Guan, I think did this comparison where he did do some resolution matching to try to see this. Not remember it off the top of my head, but I think it came out in 2017. So if you contact me, I'll send you the paper. All right, so this is just total count along the coastline. The second thing that I looked at is year-to-year variability in IBT for each of these models. So this is years on the x-axis and positive IBT anomalies along the y-axis here. And what you'll see is the 25th and the 75th percentile basically within this box. And you see some large year-to-year variability, a lot of outliers up here. And if we superimpose the two reanalysis data sets on top, we see that the models don't do so well in representing these positive moisture flux anomalies that are occurring in each year. It's pretty bad, actually. And so instead of diving into this and saying, I have 28 models, I'm going to look at the change in all 28, what I did is I actually downscaled and only looked at 7 performing models. And you can see I threw in this the Canadian model because it actually performed pretty well. And I did a few other metrics, so looking at, I think, seasonal onset, a few other things. It's in the paper if you're interested. So Canadian model, MPI, ESN-LR, French model, Australian, Italian, easier, and CCSM4. And so what I did is I compared RCP 8.5 projections for these 7 well-performing models, and basically, from this, I was able to get a better comparison to the analysis in the current climate. And the next slides are showing basically a difference between future and current. All right, so first looking at changes in AR intensity. So here we have year, so 1980, 2080 on the x-axis here. And we have average peak IBT or moisture flux along the coastline for each of these years. And you can see that there's an absolute change in moisture flux. This is expected, right? We have more moisture in the atmosphere, IBT is going to get higher. This is an absolute increase in IBT moisture flux. However, when we look at a comparison of moisture flux anomalies between the two periods, so again, I'm using a relative threshold, trying to look at year-to-year variability, we get little change in the interannual variability between these two climates. So that's interesting. But taking this a little bit further and looking at the yearly count of AR days. So again, I'm looking at AR days. This is daily data. This isn't separated into events. So AR days occurring in each year. You can actually see this increase in the number of days in certain years. So this indicates that there might be potentially greater variability in years with extreme numbers of ARs, which is concerning, particularly if you're in Southern California and you're not used to that amount of rain in one season. Okay, and last slide. So finally looking at the change in AR frequency for these models compared to the model mean. What we're seeing here is the change between end of the century and historical. And what we see is a consistent pattern of increased frequency equatorward to the historical distribution, but also a broadening of this distribution compared to the historical. And so there's a few things to look at here. So first, you kind of have this competing effect where, you know, these atmospheric rivers are kind of more variable than the coastline. But later work from Christine Shields showed that, you know, this equatorward component that we're seeing right here in most of the models is actually tied to strengthening of the subtropical jet. So this is a pretty interesting result that, you know, kind of, you know, you look at the position of the mid-latitude jet, you know, it says one thing, but you also have this component that is very important for air location. Okay. So with that, just because I'm here, any questions?
Sorry to ask a lot, but
Yeah,
it's really
sure.
interesting. You mentioned at the very end that you see an increase in the moisture flux, or IVT. And you said, well, it makes sense because water vapor is going to go up. But I'm wondering, couldn't there be a compensating change in the dynamics? How much of the strength of that is due to variability in Q versus variability in V?
That's a very good question, and something I explored a little bit in this paper as well. So what you see across the board is a pretty large thermodynamic response. So, you know, it dominates across the schools. But there is that small dynamical response that you do see kind of in the southern part of the domain. There's a very good paper out of Ruby Long's group, Gao et al. 2015. There was like, I think 3 of us had papers come out at the same time in 2015. So I think his paper did a very good job of decomposing kind of this breakdown of IVT, because it's kind of a nice, you know, an AR is kind of a nice a variable to break down, just because you do have this saturated feature, so you can't break it into thermodynamic and dynamic responses to learning.
I was intrigued by, I think, the composite that had the isotachs from the jet in red at some point, and you don't have to show it again. But what seemed to occur there in the strong rivers is that the jet was deflected poleward while extending zonally. And that's one of the major modes of variability of the jet. So can you comment on what you found in the models with respect to jet variability? Because that seems like that would be a major contributor to what the model tells you about current atmospheric river distribution and certainly future ones.
Yeah, I'm trying to think, because I did look at that. I can't remember. Can I get back to you?
Sure,
But it's a very
yeah.
good point.
Sure.
Yeah, it's definitely something that should be looked at.
Okay, because Maria Madsen's working on that for her work right now, is understanding the variability of the Pacific Basin jet
Right.
at the tropopause, and I think this is really strongly tied in here in some ways.
Oh, yeah, definitely.
Have you looked at the relationship between the frequency of the rivers and the MJO?
I did, and I would say I did it very poorly. And so I was talking earlier today about better ways to do that, and so you have an expert here who can likely answer it better. I looked at it, I didn't see anything. I was also doing it not correct. There is some research that's coming out of, I can't remember what university she came from, but she's at Lawrence Berkeley right now, Yang Zhao. And she came up with a way to look at life cycles of ARs, and so she's able to tie that to MJO variability. Of course, this is over the North Pacific, so yeah, that's as much as I can say. But there is some evidence that there is a relationship.
So you showed a figure that had all the different approaches for diagnosing the atmospheric river, and it had at least a factor of 2 for most of them, and in some cases an order of magnitude different frequency.
Which figure was this?
It was the number of total counts for the various different approaches when you were looking at your...
This segment?
No, it's way back. I mean, it was just definitions of atmospheric river.
Oh, yes, my nice little plot, right?
Yeah.
Yeah. Here,
That,
this one,
one more fold.
this one,
One more fold.
this one.
That one.
Yep.
So your count, you go from
Oh,
200, yeah, orders of magnitude different. So is there some, and that's gonna, if you do statistics on that, you're gonna get really large differences in statistics.
Very much agree.
And I know that's why there's this working group, but where are you at in terms of saying, is there a consensus approach or?
Well, so the work that we're doing right now is, starting to look at, okay, yeah, we have a lot of variability right here. Some of these are fit for certain applications, some are fit for other applications, right? So if you're interested in impacts, you probably want a pretty low threshold because you want to see all of the possibly associated precipitation that's occurring with the landfalling AR. And so what you have along the West Coast is you have these inland penetrating atmospheric rivers. And so, where is he? So John Rutz, right here. So he identifies 9,000 plus air, landfall conditions for this data set, right? That's a lot. But what he's interested in is this effect to the intermontane west region, right? So, so I'm talking about the discussion last week was about coming up with a scale. So restrictive, less restrictive. What are things that we can tell along this spectrum?
So you might be able to sort those based on some,
Yeah.
they're measured different criteria. Exactly, okay.
But along those lines, Ashley, is some of that discussion losing the focus of what's really the interesting phenomena here? Because I don't mean to say anything that that strikes anybody the wrong way, but what's interesting about these things, of course, is that they're connected to a large-scale circulation and that they do have an impact. And if you emphasize one or the other, it seems like you're talking about a different animal. So how do you sort that? I mean, that's what your group's trying to sort out, but how do you do it?
So my idea for it is, I'm interested in dynamics, right? So my idea is if there is some sort of way to look at the correspondence of identified dates between something that's very restrictive and something that's less restrictive, we have agreement, right? And so we have agreement on landfall date, and then potentially we can get this precipitation map from this less restrictive algorithm. And that way we can get at both, I would say. Now, in terms of, things where they don't agree, I think that's a good area for research. Can we take this definition that's kind of ephemeral right now, and can we put some actual numbers to it? Are there common features that we see for kind of time steps that are basically in agreement, have consensus agreement among all of these algorithms? And then where are the pitfalls? Where are the ones where not many algorithms actually identify a feature? Okay, are we identifying something else, right? What is this physical feature that's causing this uncertainty? So that's how I see it.
Yeah. It reminds me in some ways, if I could just follow up, and it'll probably be another question, but it reminds me in some ways of the agony that the community underwent from about 1930 to maybe 1970, maybe even longer than that, arguing about what's a front. Because at first they were very useful ideas, and then, we sifted through the identification of them to really get to the core processes that matter.
Right.
And it seems like maybe, do you think there's an analogy there?
I don't think so, because
Okay.
we, at this last meeting, we brought up, what's the IMULAS, the cyclone tracking intercomparison. Can't remember the name of it. But anyway, people who were involved in that project were like, lessons learned, we're not doing this, so let's move ahead with the science questions. Yeah.
I'll fill my one more. This comes to really at the heart of what these actually are, and maybe somewhat related to John's question. It seems to me, people talk about the notion of a river. You think about a river basin, and that's this conduit that the water is going to flow along. But it seems to me that it's a set of processes that help bundle together trajectories that are ascending in an airstream ahead of a developing cyclone or a cyclone. And it's sort of a dynamically generated conduit that if you were to try to, I haven't done this, but you're an expert on this, is that you look at trajectories of air parcels in this, they're not continuing from the tropics all the way to high latitudes. You also have a process along the front of this frontogenesis, which is helping to feed into the moisture that's part of this conduit. So if that's more of a comment than a question,
No,
but it's just how to identify this and how should we be thinking about them.
It's a very complex problem. I did want to point you to this. So this is a very nice paper from Soderman and Stoll, 2013, looking at, okay, you know, with these worm conveyor belts, how do we decompose worm conveyor belts from atmospheric rivers? Are they separate things? Well, I mean, it's like, you know, it's part of this framework, right? But we're looking at it in different ways. And so what they showed is this very nice kind of schematic showing, you know, the association of an atmospheric river with more than one cyclone, potentially, right? So you could have, you know, multiple processes that kind of transcend just a single cyclone framework. And then this is my attempt at a schematic that summarizes information that came out of a meeting between Heine Burnley, Klaus Wiegman, and Marty Ralph, Jay Cordero, I think. So they had a meeting, each of the experts in their own field. Okay, how do we decompose these things? And so the way that they came up with it is you have a tropical moisture export, you have an atmospheric river, you have a worm conveyor belt. So part of this kind of coherent system, each describing some sort of moisture-related transport. Right? You know, you have this kind of consistent system where this atmospheric river is low-level moisture transport in the atmosphere, where you do have local recycling. Potentially, some cases you might have long-range moisture transport. You have a tropical moisture export where you have kind of this push of moisture out of the tropics. And then you have your worm conveyor belt where you get this vertical ascending airstream. So kind of part of the same system. I don't know how satisfactory that is, but excellent paper. So, yeah.
Any other questions or comments for our speaker? Zoe.
Is there any link between the predictability and the horizontal extent of an atmosphere?
So like how
large, or I guess I was thinking kind of how wide,
How wide?
or how long.
Yeah, potentially. So there's a very nice web interface out of the Center for Western Weather and Water Extremes out of Scripps that shows basically their forecast of an atmospheric river about to make landfall. I haven't looked at that in particular, but it's something you could easily look at. You know, you can kind of see this feature, the probability of the feature making landfall. And, you know, my intuition would say possibly because it would be a stronger event. So, you know, you possibly get more developed circulation around it, but, you know.
Okay, there's no other comments or questions. Let's thank Ashley again for a fine presentation.